Okay, welcome everybody to Data Platform Down Under for the month of October. So my name's Warwick Rudd. Today we've got Kevin Fiesel joining us from North Carolina, where he's going to take us through applying forensic accounting techniques using SQL and Python. Now, before handing over to Kevin, I just want to let everybody know that this session is being recorded and will be made available on the Data Platform Down Under YouTube channel. If you haven't already subscribed, that's fine. I will look at putting the link in the chat where you can join and come back and watch this session and any other sessions that we have hosted and recorded and placed onto the YouTube channel. Before we do go on, apart from this session, what I do want to just call out, so on November 8th, so not too far away, we have got a virtual session happening. It's an all-day session for Data Virtualized. You can come along here and register for the event. We've got 6 sessions for the day for you attendees, 100% virtual. We've got the 6 speakers all coming together in one location. They can collaborate and then provide these 6 sessions for you. So if you want some more learning, predominantly on Fabric, we do have one session, which is on SQL Server 2025, but a great day of learning. Feel free. I will put the link into the chat, register, and maybe we'll see you on the day. So with that, I'll hand over to Kevin, and we can get today's session going.
All right, thank you. And I'll start sharing. Now, I should warn everybody, my slides are over here. So if I start looking that way, that's because I'm looking at my slides. If I'm looking here, I'm looking right at you, chat. So with that, let's start talking about applying forensic accounting techniques using SQL and Python. My name is Kevin Fiesel. I am a data platform MVP out of Raleigh, North Carolina. By day, I work as a data scientist at a company that builds very large boats. I also have a blog called Curated SQL, where each day I try to find and link to 5 to 10 interesting posts on topics all across the data platform space. That's curatedsql.com. And if you are really interested, I do actually have a book on outlier detection using Python. I'm not really going to get into any of the content here, but if you wanted to go further and have some fun with that, I've sold dozens of copies of it. So there are at least like 5 or 6 people who are happy with the book. Nonetheless, let's move on. And I'm going to tell a story that actually did happen. It happened before I moved down to Raleigh, but this did happen in Wake County, North Carolina, which is where Raleigh is located. So what we're seeing on the screen here is a copy of WRAL, which is the TV service. It's one of the TV channels in the area, and they have local news. This is a story about transportation fraud that happened in Wake County. Basically, what was happening was there was an auto parts company that was working in conjunction with several county employees. Now, these employees worked for the school transportation department within the county. So they were responsible for school buses that would take kids to the different elementary, middle, and high schools in the area here. They defrauded Wake County of over $5 million over a multi-year period. After all this was done, this was in the papers for a while, and you can see the articles posted in 2005. So it's actually just about 20 years ago, almost literally 20 years to the day for this particular article. Several people pled guilty for both the county employees as well as the auto parts company. Several people served jail time. The county was able to claw back roughly $5 million. In addition to that, the motor parts company, Barnes Motor and Parts, paid a $2.5 million criminal fine for their actions in this. Basically, what was happening was that this particular company was working with a few corrupt county employees. They would submit false invoices for work that they did not do, and the county employees would sign off on these invoices. They would then cover up this fraud, pay the auto parts company, and the auto parts company would pay back those county employees either in cash or in things like vehicles, vacations, yachting expenses, just all kinds of expenses that they were continually bribing the county employees with. What we're going to talk about is a notion called forensic accounting. And I'm not going to get deep into the topic because I am not an accountant. I am certainly not a forensic accountant. But there are some interesting techniques and ideas that we as data platform specialists can keep in mind along the way here. So I am going to return to this real life case several times throughout the course of the evening. I'll fill in a couple more details on how people were able to find the fraud and so on. So basically, I don't expect any of us to come out of this and say, well, I've gone and found fraud in my data. My customers are defrauding us, or something is happening within my organization. But a lot of these practices and principles that I'm going to talk about are really just a matter of understanding your data, understanding what it is that we mean by the phrase know your data. So you hear this in a lot of talks. You will hear people like me standing up and telling you, yes, know your data. That's an important principle. It's one of the key principles behind being a database administrator. But we often don't get into the details of what that actually means. And we're going to talk more about that tonight. By the way, I'm going to keep saying tonight because it is night on my end. I understand for many of you, it is early afternoon. So please bear with me on that. We've got a few items. And first, obviously, is knowing your data. In this session, I'm going to use a very simplified set of data. This is not real data. This is definitely artificial. This is fully generated, mostly for simplicity's sake. That way, I did not have to fill out any Freedom of Information Act requests, try to retrieve data, rebuild a data structure that probably was pretty awful, because all real databases are awful, it seems. But this is going to give us an idea of how we can learn without having to spend the entire session talking about, well, this is what this field means in this particular table. This is just a quick view of the tables involved. And I'm going to use zoom it here to draw out that I've got roughly a half dozen interesting tables, plus I have a calendar table that I can use for date tracking and such. So we have employees. The employees are, in our case, the county employees. We have vendors, which are the companies that are providing services to the county. So they would be the ones who might be repairing school buses or selling parts for school buses, etc. Expense categories are the specific problems, the specific things that you might see. So things like windshields or headlights or brake lights or seating material, etc. And each vendor, of course, they sell specific things. So they're not going to sell everything. They're not going to, the same vendor is probably not going to repair glass and also fix the mirrors and fix the seats and fix the engines, etc. We have buses. These are the actual buses that are running along town, and line items. So a line item is when we have a repair or some operation that occurs, we track it in here. So this line item is something that happens to repair or otherwise maintain a bus, given a vendor, given an expense category, and we have at least one employee signing off on that particular expense. So that's the main idea behind what we're going at for the data structure. And we'll see this a little bit more when we dig in. The scenario is going to be just like that introductory scenario. We're going to look at external audit. We're going to look at a county transportation agency. And if all I've got is a data model and a login with read-only access, that's all I need. So let's see where we can go with this. We're going to start with some basic analysis. And when I say basic analysis, there are a variety of different approaches. And I've got several of them listed here. We are going to go into detail on each of them. So let's get going into detail. The first one is summary analysis. The idea of summary analysis is very high level data structures, row counts, data types, what kinds of relationships there are between tables, basically what we did in that image. And here are some of the things that I'm going to look at if I'm in SQL Server. I've got a brand new database. I need to learn about it. One of the first things that I'm going to look at, assuming that I have access to view this, is the report in SSMS, disk usage by table. I know this is a very old image. It's a few versions of SSMS ago, but it's still okay. So we have here All right, so we have here report disk usage by table. And what that's going to show us is for each table in this database, how many records are there? How much space does that do these set of records take? How much of that space is data and how much is indexes and how much is available? Like if you delete rows, the unused kilobytes is going to show up here. This will give us an idea of what are some of the most important tables. Now, as you're looking at your list of disk usage by table, you may see some logging tables, you may see some archival tables, you might see some stuff that's not that important. And based on the names of the tables, you might immediately understand, oh, yeah, this isn't going to be a very important table. It's not going to be important for our understanding. So we start with the biggest table that we either know will be interesting or think could be interesting. And we look at that. So driving from that one, the first one was line item because it has the most records. So driving from this thing, I can see next, I want to look at keys. Hopefully there are keys. I want to look at indexes, maybe. But I want to look at the column names, the data types. I want to get a feeling for what this table represents. And on here, we have bus, vendor, expense category, employee ID. These are all keys to other tables. We have a line item date and an amount. So I'm already seeing that this is essentially like a fact table in a warehouse. This is going to tell us what happened, when it happened, and some of the context around it happening. And thankfully, they have foreign key constraints to these other tables. Now, I'm also going to peek at a few rows, not a huge number of rows, but a few of them so that I can double check what kinds of data integrity rules we might have. I'm not going to know exactly what the specifics are, how frequently different columns show up, or how frequently different values show up in columns, etc. But this is just to give me a feeling for the table. Then I'm going to go through each of those keys. I'm going to repeat that same process. Basically, I want to spider web out my understanding, starting from this, what I hope to be the most important table, expand it out to other relevant tables and keep track of what I'm doing along the way. So if I look at buses, I see, oh, okay, bus feels almost like a dimension. This almost feels like warehousing data. And employee, same story. Expense category, vendor. These are all fairly close to lookup tables. And when I run out of tables, then I can scratch those off my list and I'll find the next biggest table, which in this case might be calendar. Or if I see, oh, this is a calendar table, and I check it real quick, yeah, this is just a regular calendar table. There's not a lot of magic involved in there. So I might go to the next thing, which is vendor expense category. And we go through all of this. And also, this may be a good case for database diagramming tools. Now, the tool that I have an image of used to be free. It's no longer free, so I'm not going to recommend it. But in any event, you can find a few different tools that are available that will help you reverse engineer a database into a diagram. And that can also give you an idea of how things interconnect. Once you have at least some of the basics, the next step is to look at growth analysis. And growth analysis is really how have things changed over time, especially in ratios over time. So our goal here would be to look for major changes that have happened that would be outside of the norm. And typically, we'll look at additive measures. So we might look at, say, company revenue or cost or number of customers, those sorts of measures. So let's take a look at that in a demo. And by the way, these demos are available. I will give you a link at the end where you can grab them. These are all Jupyter notebooks. I do have the setup instructions and everything if you want to try to play around with it. In the data folder in here, I do have scripts to build out all of the tables for the database. So you can try it along at home if you so desire. And I even have a few scripts for getting columns, data types, non-key constraints, and so on that I'm not really digging into a lot here because my assumption coming in is most of you are familiar enough with T-SQL and with SQL Server that you may get something out of this, but you're probably going to get a lot more out of the Python part of the house. So let's do that. And there we go. For data retrieval, I'm going to use PyODBC. And by the way, if you would like me to bump up the font size on this a notch, please let me know. I'm happy to do so. I am already in a virtual environment in Python that allows me to isolate out my requirements, my packages that I want to install from anything else installed on my system, Python related. And I already have things installed, PyODBC, Pandas, and Toml. Toml is so that I can load a configuration file that connects out to my Azure SQL database and has my username and password. So that way I don't have to show it to you on the screen because this is getting recorded. I am going to connect to this database. We'll see if it works. I did forget to run a script earlier to wake up the database. So if it's a serverless database that's asleep, we'll find out quickly. And looks like it's awake. So good. It is awake, and so am I, and so are you. And let's keep going. So I'm going to retrieve data from buses. And this query is pretty simple. We've got bus joined to bus model. Bus models would be the manufacturer of the bus. So we have the model, we have some measure of quality, we have some things like average road conditions, and I've got some other tables. Now I'm not going to explain the queries here. Instead, what I really want to do is look at the data and get a slice of the data. So let me see the first few buses. I have buses 0 through 4 in the list, which happen to be bus IDs 1 through 5. For each bus, we have a bus model, and we have a model quality. And that quality would be how likely is this bus to break down soon. If it's a higher number, it's more likely to stay in good shape for longer. So that's the general idea. Average road conditions, this would be maybe for that particular bus, what kind of driving are we doing? Are we doing a lot of unpaved roads? You're on very rural roads. Are we talking about uh, say well-preserved suburban areas where you have a hard speed limit? Are we talking a lot of freeway driving, etc.? So a lot of potholes. It's just a number that I came up with to give us some flavor to the idea that not all buses are going to break down at the same rate, and there are reasons why they may break down sooner. When it first went into service and when it was retired. So some of these buses have been around for a little while and some of them have been retired. So we've got that information in the bus table. I can use the describe method to explain each one of these attributes. And what's nice about this is if you have a non-numeric attribute like bus model, we see the top, we see the count, we see the number of unique, and we see the frequency. So how many of them show up? We have 5 bus models. We have 1,560 total records that have bus models. By contrast, if we have a numeric value, so let's pick model quality. Model quality is a numeric value, so we're going to see the mean, the standard deviation, as well as a 5-number summary. This 5-number summary includes the minimum and maximum values for model quality. It includes the median value, that 50th percentile midpoint, as well as the 25th and 75th percentile. That's known as the interquartile range. This is the middle half of our data. And so we want to see how spread out that middle half is. So these 5 numbers give us a lot of distributional information about the spread of numeric data in our data set. I can also look at the D types property, and this will give us the data type for each one of these columns in this pandas data frame. So buses, let me just scroll back up. This is a pandas data frame that comes from reading a SQL database. I know it's pandas because PD is how I imported pandas. So I realized that I did not talk through that bit immediately, and I figured I would come back and briefly describe it. So we have our data types. We have 64-bit integers, we have 64-bit floats, and we have objects. Pandas and Python don't really have strings and date types and so on. There is a date time type. There are actually a few date types, but by default, pandas will take dates as more of strings, more of suggestions than as, strictly speaking, date types that we would perform date math across. So I can change it to a date time by using the toDateTime method. And so we'll do that for date and first in service and date retired. And now I'll describe these attributes again. And notice that after changing these two from strings or objects to date time types, and by the way, if I rerun date types, we see date time 64. So now it is a 64-bit date time that is valid down to the nanosecond. We can see now that we have minimum, maximum dates. We have 50th percentile of date, etc. So that's pretty neat. We are able to convert this data type and get more relevant information out of it. And I have some key takeaways in case you're following along at home and want to see what I'm seeing. There are 12 employees in total here. So these are our 12 employee IDs, our 12 names of the people who were involved in this. And if I look at expense categories, we have a variety of things. Like I mentioned, this is all different types of things that can happen to a bus. Maybe we have vehicle repair, maintenance labor, we have fuel, we have lights, electrical, seat repair, wheelchair tie downs, etc. There's a lot involved, and we're not going to get into all the details here. Suffice it to say, I did in fact copy and paste that from an actual website where they were selling different parts. So I strive for realism. We have, speaking of striving for realism, here are my vendors. They are all fake for obvious reasons. So, we have all the vendors. There are, looks like 15 of them in total. And all these vendors, they have their own specialties. Like you would figure fuel suppliers is probably mostly going to sell fuel. They're probably not going to sell filters, OEM body parts, etc. They're probably going to focus on one or two things. And that's where the expense categories come into play. So we have, for example, this particular vendor is going to do vehicle repair labor and vehicle maintenance labor. They don't sell parts. They help fix vehicles. So that's the general idea. They would go to a different source to get the parts. And I can take the vendor expense category. So I'm going to take the vendor name and expense category, and then I'll group it by vendor name. I'm going to get the count of expense categories, and then I'd like to sort this sort it descending. Ascending equals false. That tells me I have this vendor, Safety First, who is in 12 different categories. So they have 12 different offerings that they provide. And Tony's Fixer Upper Buses has 8, and so on. We've got a few of them that only do one thing. Fuel Associates, Fuel Suppliers, they only do fuel. If I sort this by vendor name, in this case, by default, ascending is true. So we have expense categories and how many different vendors are authorized to provide services. And if you're looking at, for example, government accounting and you're looking for vendors in a set and we see one vendor, it's not a red flag, but it's like a yellow flag, maybe a dim yellow flag. It's not a very bright yellow one, but it is still interesting to see that for some of these services, we only have one vendor who can provide that service, and that's usually not a great thing. But in other cases, we may have 3, 4, 5 different vendors. Finally, just a quick idea of line numbers. So my line item date, I'm already switching that to a date time so that we get the best information, and we see details on the line item ID. It's a unique ascending ID, so there's not going to be a lot of intelligence to gather from this. But we do have our dates ranging from 2011 to 2022, so that gives you an idea of our time period for this data. We have bus IDs, expense categories. All of these are identifiers, so we don't necessarily gain much information from percentiles of an identifier. Amount, however, we absolutely can. We can see that the minimum amount is $0, the maximum amount was $3,300, and our 50th percentile, our mean, is $109 per line item. All right, so that was summary analysis. Let's take a quick peek at growth analysis, because I did talk about that in the slides. So what I want to do is check first on buses. So let's bring in our data set and let's have a query of buses. This is going to be calendar year and number of buses, and we're going to break this out by calendar year 2011 through 2023. and let's build a line plot using the Seaborn library. Seaborn is not necessarily the greatest library, but it allows me to get a line plot in one line, so that's good enough for this preliminary analysis. We see roughly a straight line. That's kind of what I like to see. I like to see straight lines. So everything looks pretty solid there. It looks like they are regularly bringing new buses into service. And as buses rotate out, we have new ones coming in. So no big deal. Now, invoices per year. What I would expect is we have some number of line items. Now, each bus is going to have its own maintenance issues, and we can't guarantee that there's going to be exactly 12 invoices per bus per year, but we kind of have a feeling for if you have more buses, you're probably going to have more line items. And if you increase the number of buses by this much, we're going to have some multiple of that much as the increase for line items. So there should be kind of a collinearity. As one goes up, the other goes up, and they're going to follow along reasonably well. That's my conjecture coming in. If I look at this data, I see something weird. This is my first weird thing that I see, because up to this point, we do have roughly a line that roughly growing at about the same pace. Then we have this enormous jump up for a few years. And then we have a drop. That drop is weird. So we have something. Now, at this point, that's a yellow flag. That's like, hey, that's weird. Let me look more into it. So what I'd like to do is compare invoices versus buses. And you look at this and you say, well, I mean, that's basically a flat line. You can't really see anything. So let's instead, and by the way, here's the code that I use to show this. So I'm concatenating together the annual invoices and the active buses onto one plot. And I'm going to build a line plot, basically combining together invoices versus buses. I want to have calendar year as my common axis here, as my x-axis. The y-axis will be the value, and my grouping is going to be based off of the variable. So whether that is number of invoices or line items versus number of buses. But again, this line isn't helpful. It's not showing us anything because these two are not on the same scale. So we need to rescale. And I can use that from scikit-learn. There is in pre-processing a min-max scaler. And what this will do is it's going to convert the smallest data point to 0.0, the largest data point to 1.0, and maintain the distribution of data along the way. And where that gives us a benefit is that we can then plot both of these on the same plot and have the same axis. And what we see is that there is something that is kind of close up to right around that point. But then there's a major phase change right here where we go from not quite linear growth in number of line items versus number of buses to way higher than linear growth. And then it kind of levels off a little bit, it levels off, and then it actually decreases a bit. So again, this is showing us that it's kind of strange, especially because we do have a mental model of how number of buses should affect number of invoices or number of line items. And we can also build something called a QQ plot, a quantile plot. So the idea here is I have two variables, number of buses, number of invoices, and then I can order each variable, smallest to largest. And so what I want to see is basically a scatter plot of ordered sets of points, number of buses, number of invoices on this point from smallest to largest. And this is both scaled out to 0.0 to 1.0. So we're still using this min-max scaler from above. And what we would ideally expect is we're following closely to this line because we believe that there is roughly a linear relationship between number of buses in service and number of maintenance issues or line items that we're going to fill out for our buses in service. And we do see up to about 55 to 60%, we do see that happen. And then there's this big jump. Kind of have this big jump right here. And so below that point, we're basically below our identity line. Above that point, we are above the identity line. And that's another way of rephrasing what we've been seeing, that there might be something going on here. There might be something of interest. Now let's look at expenditures per year. So we want to see not the number of invoices, but the total invoiced amount. So the sum of amounts. And we're going to plot that information as well and see, oh, it has a similar pattern. So we are seeing a similar hook shape in our data. All right, correlation tests. There are a couple of them that I can show. So inside of here, I've got yearly data. So now I'm grouping data by year and removing out the duplicated calendar year column. So I'll remove that column and then show this correlation. So we have calendar year, number of invoices, number of buses, total invoiced amount. And we see number of buses has almost a one-to-one relationship with calendar year. That another way of saying this is we bring in roughly the same number of new buses every year. So maybe like 15 a year, 20 a year. And this county is just extremely consistent. Every year they bring in 15 new buses. The number of invoices, the total invoiced amount, not quite as good of correlation. But a little hard to read this as in numeric form. So we can build a heat map using Seaborn. And here's our correlation. We can see that if you look at the diagonal here, this diagonal basically just represents the variable itself. And then we have our relationships. So let's say calendar year versus number of invoices. You have the diagonals that kind of represent the same bit of information. We have a mirror here, so I can look at this bottom side of the triangle and get all of my information. All right, let's now bring in more data. So we've seen just a couple of data points, but I want to bring in addition to the calendar year, the number of invoices, the total invoiced amount, I want to get maybe expense categories, number of years the bus is in service, maybe the bus model quality, some of these other pieces of information. So I'll do a correlation again, and I will set numeric only to true, and that will allow me to only include the variables that are numeric in nature, because correlation doesn't work on strings or non-numeric features. And we have, again, a mess of numbers. I'm not even going to try to analyze the mess of numbers. Instead, let's plot it, and you can see this heat map here. So there are a few things, like bus ID and number of years in service has a strong negative correlation. That makes intuitive sense because bus ID is an auto-incrementing number. So the older buses are going to have lower numbers. There's nothing special to that. Calendar year, bus ID, similar story. Calendar year, years in service, similar story. So there's not a lot. Most of these are near zero. There's actually not a lot of correlation in this data. And the last bit is called a KS test. It's the Kolmogorov-Smirnov test. And I've probably mispronounced it. It happens. But the KS test is an idea of whether or not two data sets seem to come from the same source. And we have above seen this hook. And so I'm kind of wondering, what's the likelihood that this data source, let's say prior to 2018 and later, is actually the same data? And so I can grab this information, 2011 to 2018, or calendar year equals 2022, because it seems like there's this drop. And if you actually draw the line, if I draw a line that kind of follows this, you can see we end up just a little bit above in 2022. So it feels like 2022 is like a major turn back toward that line. So that's why I want to include that year as well. So if we compare those and then the dates for 2019 to 2021, and I run this analysis, I can get some statistical result. Now our p-value in here is 1.15 times 10 to the negative 86th power. Anything below 0.01 is a decent indicator that this is not the same, not drawn from the same data set. The statistic value in here is 0.3, in this case 0.3125. When I originally ran it was about 0.305. And I have a little bit of calculation. If the statistic value is above 0.04, distributions are probably different. This 0.3125, definitely above 0.04. So we would expect that these may actually be drawn from different sources. So I'm going to finally say, by itself, what I've shown you so far, there is no proof of fraud. There's no proof of anything hinky going on. It could just very well be that the underlying data has changed. So this is a something I want to push over and over, that just because you see something change doesn't mean that fraud is the cause. Most likely, the underlying circumstances have changed. So we want to always have that in mind as we go through this. Now, sometimes it's not the data points themselves that are interesting. It's the gaps. It's the things that are missing in the data. And like if you have receipts, you have purchase orders, check numbers, invoice numbers, those sorts of things. This is where accountants and auditors hate to see gaps in data. Like if you have check number 1001, check number 1003, the auditor is going to ask, hey, where's check number 1002? I don't know. My system, I guess there was an error and it ate number 1002. Accountants don't like that. Auditors really don't like that. So if this is intended to be a number that is valuable for an audit, we can't just use something like an identity integer, because if you have a rollback, you have an error on insertion, that number's gone. And so for the purposes of an auditor, they don't like to see that, because the reason they don't like to see that is if you have gaps in data sets that should be contiguous, that is often a sign of fraud. It is often a red flag for fraud that, hey, you've hidden something here. There should be information in here. You should have an entry for this, but you don't have an entry for this. And now I need to go see if I can find some other record somewhere else that can figure out what has happened with that entry. Was it a check that was actually voided and didn't really have any use? Or was it a check that somebody wrote and cashed and didn't put into the books in the hopes that someone wouldn't later reconcile the data and find, where did that $12,000 go? So this is something that we would normally want to look into as accountants, as auditors. These are the types of things we might look for. So I'm going to check out this particular notebook. Now this one was an Azure Data Studio notebook. It was a SQL notebook. We don't have those in VS Code. RIP Azure Data Studio. But I do have the ability to run queries in VS Code from here. So I will just copy and paste this. What I've got here is the current line item ID, and then I'm using the lead window function to get the next line item ID from the line item table. And what I'm looking for is my current line item ID +1, next line item ID -1 as range end, and I want to see where there's a gap, where there's more than one data point difference. And if I run this query, what we end up with is that it looks like 6 and 7. So 6 and 7 are missing. 14 is missing. 20 is missing. 199, 200, 201, 202 are all missing. 339 through 341 are missing. These are all line items that do not exist in this database. So something has gone on that has resulted in these particular line items disappearing. That could be just as simple as our application tried to insert an invalid value and we rolled back the transaction, and so this ID is just gone. But it could be a sign of something more serious if this line item ID is supposed to be business relevant. So this is the difference between a non-business relevant surrogate key where if I skip a value, it doesn't matter. It's a surrogate key. It has no business use. Versus a business valuable key that needs to be contiguous. And we can also see, I've got a couple of other queries if you're interested of different islands. So looking at customer invoice bus days. So I want to see what combinations of items do we have. So let me just run this query and we'll see the results. And then I can quickly talk about the query itself. We have here for this bus, over this 5-day period, we had a line item, at least one line item. So for this particular bus, we had 5 days. Looks like we've got quite a few where there were multiple days in a row. So this might represent something like a bus was out for a long period of time and we needed to do repairs over the course of multiple days. And so that's what this query is going to give us. And then our next one is vendor invoice days. So vendors sending invoices over specific date ranges. And I just paste this in and run it. What we see is everybody has 5. That's a little bit weird, but honestly, it's just something that was an artifact of the artificial data. If you saw this in a real data set, you might say, huh, that's weird. Until you thought really hard and said, wait a minute, do they work weekends? Because if they don't work weekends, then yeah, we're probably just going to have 5 contiguous days as the max. So something to keep in mind. That's the idea of gap analysis. And I will note here, this was my warning that I gave earlier. If you're using an identity integer for something that needs to be gap resistant, it can be a problem. Same thing goes with sequences. A sequence will behave exactly the same way. And depending on what features you have set on, you could lose 1,000 IDs for a sequence just from restarting your SQL Server instance or whatever number you set that to be. It's not a big deal. I mean, it's not the end of the world or anything, but for auditing purposes, then it could be a little bit of a deal. Unfortunately, if you do want a gap resistant mechanism for inserting numbers, best I've got for you is to go in serializable mode, lock the table until you have control, you have inserted successfully your ID, and then unlock the table at that point. And that way nobody else can insert your same ID and nobody else can go grab the current ID until the next one is in. It's going to be slow. It's going to basically make your application single, or your database single threaded down that path. But that's what we would need if we absolutely needed to go down that road. Alternatively, there may be another mechanism for your particular application and circumstances that would work better. But let's talk a little bit about regression. A regression analysis, putting this as simply as I can, we have a few different things. We have a dependent variable, the thing that whose behavior we want to explain. We want to understand, for example, number of invoices per time period. Independent variables. These are the things that we believe will help us explain the dependent variable. Number of buses, maybe the road conditions, maybe the number of days of schooling, how many days or miles of driving are we doing, etc. And then we need data points that relate those independent variables to the dependent variable. So we need to have information. If we think number of miles driven is a key factor, we're going to need to know number of miles driven for that time frame. And if it's on a per bus basis, which we would expect this to be, we would need to know number of miles driven per bus per significant time period. Regression analysis, there are a lot of rules to it. There are conditions around when it works, what kind of regressions you can make, the relationships between variables. There's a lot going on there I'm not going to get into, but if you do want to know what your data ought to look like, and I do put ought in scare quotes because regression analysis is a model, and all models are wrong. Some models are useful. So I don't want to give you the idea that, well, the regression says it should be like this, and therefore it must be like this. That's confusing the map for the terrain. But as soon as I say that, I get to this next slide where this is a screenshot of a slide from the CPAs who actually found the Wake County transportation issue. This maps the number of buses in service for the county over time, and this axis is the maintenance cost in millions of US dollars. So you see here, up to about this point, you have either something that's linear or slightly sublinear, where more buses, we might have economies of scale. By having more buses, we get better deals, we get better discounts. So that can actually decrease the overall cost on a per bus basis. And then we had that data point right there. So their straight line puts us roughly just over $6 million, and this was about $7.5 million. It's a $1.5 million difference. My sublinear line might actually put it somewhere closer to here, where that's about 5 million versus 7.5. That's about a $2.5 million difference. Either way, that's a pretty substantial jump for that one data point. So the benefit here would be that if you do have some reasonable model for regression and you see a point that is radically off from expectations, that may be an indicator that there's something interesting to look into further. There will always be noise. There will always be movement um, away from your model line. So just because there is noise doesn't mean that there's something there. But in this case, that was so dramatic. It was so drastic that the auditors basically built a regression line and said, "Oh, I think there's something here," and it turns out there was something there. And you might ask, well, why didn't anybody catch that earlier? It happened over the course of multiple years. The reason is that this county had not been audited for several years. And during that time, this is when all the fraud happened. So it wasn't until there was an external audit that somebody caught this pretty quickly. So let's take a look at regression of expenditures against number of buses. I've got my calendar year and month, road conditions, the bus model and model quality, the number of years the bus has been in service, expense categories, total amount, number of line items. So I've got a lot of information on here. And what I'd like to do is build out a simple linear regression. And I'm going to use as my input data the calendar year and month, the road conditions, the bus model and model quality, the number of years in service, the expense category, the vendor name, the employee name. So you'll see here, this is not just numeric data. I can include more than just numeric data in my analysis. The way that I can do that is the mechanism I'm going to use is called one-hot encoding. And basically what this does is it sort of pivots the data. So if I've got 12 employees, I'm going to pivot that data so that I've got essentially 11 new columns. And my 12th employee is kind of hidden where if all of these values are false, like is this employee 1? No. Is this employee 2? No. Is this blah, blah, blah? Employee 11? No. Okay, you are employee 12. That's how I get to 12 employees, even though I only have 11 new columns. But we create that pivot, and we do that for each non-numeric column. So that's what I'm doing in my one-hot encoding. My dependent variable, the thing that I want to predict, the thing I want to understand, given all of this other information, is total amount. And so I'm going to break this out into a test data set as well as a training data set. My training data set is how I will develop my regression model. My test data set will be how I can evaluate the model on data is not yet seen. And so I'll build a simple ordinary least squares regression model. This is probably not a great model, but it's okay. We're just doing this for the purposes of learning. We're not going through a data science course on regression analysis. We get back a lot of information here. And yeah, there we go. Starting at the top, R squared, it's basically how close of a fit do we have overall in our data. This will range generally between 0 and 1. you can technically have a slightly below zero value in certain circumstances that are beyond the scope of this discussion. 0.551 is probably not that great. It's okay, but it's not great. If I go down and I look at each of these, what this is telling me is this coefficient multiplied by the value of calendar year, multiply that by 1.11, and that's going to give me my weight of calendar year versus line item amount. You'll notice that this is positive. What that's saying is we have more money that we're spending on an annual basis, all other things considered, all other things equal. And so we have some people like this model, this bus model, Neoplan AN 440. It seems like if you have that particular bus, we have less expenditures. If we have the Easy Rider, it is not quite as low. If we have different expense categories, exhaust is more expensive. So an exhaust problem is more expensive, whereas if we are looking at maybe like heating and defrosting problems, they're less expensive. So we can look at this and get some simple idea of how these numbers relate. But there are a lot of variables here. There's a lot to try to understand and unpack. And so there are other mechanisms that will help us understand the quality of our model. One of those is called mean squared error, and its child, root mean squared error. Mean squared error basically says, from my test data, here is what my trained model predicts you should have for total amount, given these inputs, given these independent variables. Then we compare that to what actually was there, and we take the error, the difference between those two, we square that, and then we take the mean of all of those items, all those squared items. And that's 30,818.91. Now, that's in square dollars, so that's not something that's intuitive for us to understand. But if we take the square root of that, we have this measure in dollars. So our total amount of an invoice, we're off on this model by, on average, about 175.55. So 175, 176 US dollars. So that's interesting, but it is a pretty high error. So not a great model. I wouldn't trust this model. But what happens if I look just at pre-2019 data? So I look at 2018 and earlier, and we build roughly the same type of regression analysis as before. So I build out that model summary. There we go. We've got our data here. It's a very different data set, but R squared 0.56. It hasn't really changed. It's not that much different. If I look at root mean squared error, $174. That really hasn't changed at all. So slight difference, but not a big deal. But then we look at 2019 through 2021. So calendar year between 2019 and 2021. And I build out, we have a root mean squared error of $188. So that is higher. We do have more of a difference between the two. And I can look at this data, the actual amounts versus the predicted amounts, just to get a feeling for, on that data set, what we did predict and what we actually got. And you see the dollar amounts here aren't that high. So being off by $170, $180, that's a lot. We're not doing so well in our explanation. But in aggregate, predicted amount, $1.58 million. Sorry, $15 million. Missed a comma. So $15.8 million. Total was actually $18.2 million. That's a good almost $2.5 million difference for this. Basically looking at 2019 to 2021 versus what we would have expected from a straight line. So if you go back to the earlier picture where we had the big hook, the straight line says that's about a $2.5 million difference over the 3-year period. If I look at predictions by employee, I see differences. I see a few employees have these major differences, like $600,000 differences for these 4 employees. Everybody else is relatively close, within 5, 10,000, maybe $20,000. That's, again, not proof of fraud, but it is very interesting. It's quite interesting to see, why do we have 4 employees whose behavior is roughly an order of magnitude different from everybody else? So we might want to ask, we might want to try to find an explanation, and we'll keep digging to see if we can find the explanation. But breaking this down by expense category, glass windshields and windows is off by $1.4 million. Mirrors is off by 400K, and everybody else is kind of flopping in this area. We're high on a few things, but once you get down to about vehicle repair labor, everything's within 5 digits US dollars. These 4 are significantly higher. So again, might be looking at what's going on here. If we look at this by vendor, we have one vendor who is 2 orders of magnitude different from everybody else. That's weird. That's quite weird. Now, glass and accessories, we already see that glass happened to be the big difference in here. Mirrors, which are mostly glass, lights and reflectors, glass components there, possibly. And so we might see something interesting for there. And then there are other algorithms. I won't go through this. Basically, I showed, in this case, it's light GBM. This is came out of Microsoft research. It is a gradient boosting model, and it turns out not to do much better than linear regression. So we're just going to leave it there. You're welcome to try this out if you'd like. If you look at the per month line items, there's an improvement. It's a little bit better, but it's still not fantastic. So let's keep going. Talk cohorts. And there are a couple of concepts here in cohort analysis that I do want to get into. If we look at the high level general ideas, the customers, the vendors, the groups, looking at this at that level may help us find problems. And one angle is duplicates and cardinality. So I'm thinking of duplicates in 2 separate ways, 2 very different definitions. One of them, if we have a one-time code or a unique key that's not enforced, we might see multiple entries for the same thing. So same data shows up multiple times. That may be an indication of somebody trying to sneak things through. Second, you have things that are close but not exactly the same. There was a case a few years back, it was probably like 6 years back at this point, about a big bank fraud issue where a lot of money was taken through the SWIFT system. In one case, a German bank actually caught the issue and did not send the money. I think this was out to Bangladesh. That was where the bad guys were. They did not send the money out because the company that was supposedly putting in the request to send money had misspelled their own name. They had fundation instead of foundation. So in this case, we did not have the same entity. We did not have the same value. We had 2 different values. So we were looking at cardinality in that result, in that instance. There are different ways that we can calculate similarity of text phrases. You have some classic calculations, Levenstein distance, soundex, pattern matching. These things exist. You're welcome to dig into that some more. If I go to the weight counting case, this is a slightly different concept of duplicates. There were 24 separate days. This is real life data. 24 separate days in which the auto supplier sent 50 plus invoices. All of them were under $2,500. Now, what is special here is at that time, any invoice under $2,500 required one person from the county to sign. If you had an invoice over $2,500, you needed 2 people to sign for it. So instead of batching things together into a relatively small number of invoices, they sent out a large number of invoices, all of which happened to be just below that threshold where we needed a second person. That's a red flag. That is something that an auditor can and should look at and say, this is weird. This is very weird. And Now I'm going to ask questions about why these numbers are all so close to 2,500. So let's take a peek at that particular demo. All right, bring in our data, look at invoices by day. And we have one invoice on a given day. Now this is per line item date, so per day, per bus, per vendor. Vast majority of the time we have one invoice for a bus. Sometimes we have two invoices. 3 instances we had at 4 instances we had 3 invoices. One time we had 4 invoices on the same day. So most of the time you have one invoice per bus per vendor for whatever date. And who had those duplicates? And we see that there are a variety, like everybody's got some duplicates. So that's not weird. We do see 2 orders of magnitude difference for these 2 vendors, but it's not that far off. I mean, yeah, you're talking like 200 versus 100. But if you look at a distribution of data, there's always going to be somebody who's out at the edge. So now let's look at distinct values in the data set. And I can use the apply function in Python to apply a given function across every column in my pandas data frame. So in this case, I'm going to use number of unique records per column in this data frame. And what I get back is I get 12 years, 12 months, 1,500 buses, 38 average road conditions, 5 bus models, 16 years in service, and so on. And then 61,000 values for amount. So looking at this, I can see a lot of this stuff looks like it's lookup data. It's the type of thing that you would expect to see a drop-down list. Oh, vendor, select from the list. Expense category, select from the list. So most of that pretty straightforward. Bus ID might be something you type in the ID or something. The amount, obviously, that's a number that you type in. So that's probably going to be different for item to item. And let's look at high value invoices. So let's suppose we have in our scenario, for our county we're looking at, our cutoff is $1,000. If you're above $1,000, you need 2 people to sign. If you are below $1,000, you only need 1 person to sign. So we're going to look who is close to 1,000 without going over. And these are unique values. So we have 1,000 buses, 2,999 unique amounts that are below $1,000. And 12 of our 15 vendors have at least one invoice that was between $850 and just below 1,000. So let's look at how frequently this comes up. We look at these, and a lot of these vendors have several hundred. So that's just a regular mixture, nothing too special. This particular company is 645, but they might have some fairly expensive invoices. They may be working on some engine work or something that's a little bit more expensive on average. So let's look instead, $995. If you're at $995 and just below 1,000, it's a little bit weirder. We do see this particular company. We did see them before at the regression. So they have 54 items that are just under $1,000. And if I look at all, most of these are $999.99. Some of them are just a few dollars off. They're a few dollars less, but almost all of these are right at that edge. Now, let's look at how often anybody gives us something that's more than $999, less than 1,000. And we see one company does it all the time. Other companies have had a few instances. But this is more than everybody else combined. So that's interesting. Maybe a little bit weird. But maybe they're working on say windshields that cost $900 to $1,200, let's say, hypothetically. So let's look at how they're doing above $1,000. And they have 19 total invoices. You have other companies, like we saw this company here. They had a lot of $850 to $1,000. Well, they also have more over 1,000. So these guys are have a lot over $1,000. But these people don't. They only have 19 total that are above $1,000. So they have more that are $999.99 than anything $1,000 or more. Again, it's not proof, but it's weird. It is another flag. The flag is getting redder. We at least have a pink flag. If I look at amounts, this is kind of grouping that, where earlier I just showed you the list and it was like, oh, there's a lot of these. It turns out there are 46 of them. So let's look at this by employee. Who among our employees is consistently seeing between $900 and $1,000? And the answer is everybody. We're seeing we have a nice split here. So let's key it down. Let's just look at Glass and Sons. So we can use vendor name starts with, and that's sort of like the like operator in T-SQL, and say starts with Glass and Sons. Amount is greater than or equal to 900, less than 1,000, and we'll group this. And we have exactly 4 people. Now, but at the same time, maybe these are the 4 people who always work on Glass and Sons, and they don't, and nobody else works on them. So let's look at every case of Glass and Sons, and I mean the 4 people show up like 4,000 items a piece. Everybody else is 300 something items a piece. So all 12 of them have handled invoices, but these people are averaging. You look at this. This is a 4 to 5 per day for this one vendor. That's a lot. So let's compare. Let's compare 2011 to 2018. And I should note here, this was specifically just for 2019 through 2021. So let's see how they did in the other years. It could be that these are the 4 people who always work with this vendor, and maybe they're on vacation and somebody else comes in, something like that. And we look at this, and no, outside of that 3-year stretch that was already showing up as a bit hinky, their behavior is the same as everybody else. So what happened in that 3-year period that made their behavior radically different from everybody else's? That's weird. The flags are coming in. Another type of analysis we might look at is difference analysis. So that would be differences between maybe vendors or differences between groups. This is number of invoices per month and year. And on a per year basis, we see this is just basically a different way of representing our data using a box plot. And we have this relatively slow growth and then this massive increase in the next year. So that's a little interesting. We also have outliers. Now, outliers, we can define them either in a technical sense of the term, and again, I have a book on that if you really want to get into that detail, or well outside of the norm. This looks weird, and looks weird is a reasonable indicator for an outlier. Turns out humans are pretty good at detecting outliers in certain circumstances, especially with visual indicators. But again, real data sets will always have outliers. So just because something is an outlier doesn't mean that it's necessarily anything that's suspicious in and of itself. There will always be a max. There will always be outliers. Now, where things might be interesting is this clustering behavior. We saw a little bit of that with coming very close to that $1,000 but not going over. And let's check a quick peek at cohorts and clusters. So I'm grabbing a bunch of data again. Poor DBAs having to manage people like me writing these queries against their databases. But take a quick reminder of the issue. So we're going to see if we can explain any of this. Why we have this big hook. So let's break the data down by time. And here's my box plot. This is breaking out similar information, but I'm looking at the story a little bit differently. And I'm looking at ranges of data. So you see here relatively tight ranges for each of the first several years. So we have growth. We have that the boxes are moving in an upward direction, but they're relatively tight. Then for 2019, we have this gigantic leg. And the leg here represents this blue box is our interquartile range. That's the 25th through the 75th percentile of data. This represents anything that's 1.5 times the interquartile range. So basically this line times 1.5, move that down. Any point within it is in this whisker. So this is our whisker. Our whiskers are pretty big. Whiskers are big. Whiskers are big. Hey, whiskers got small again. That's weird. So we see this behavioral change over the 3-year period that reverted after that 3-year period. Now, if I look at number of items, this is a number of line items per month plotted as a scatter plot. So I'm showing each of the 12 months on here and staggering the data so that we see the monthly points. So we do see, it looks like up to maybe right about here, maybe a little bit higher. Maybe these points are part of this, but we do see definitely there is some cutoff point somewhere around here where the pattern changes. We have this big increase, whereas before we had kind of this smaller increase, and then we have this little box out here, this little cluster. But during this point in time, we have a radically different behavior pattern from everybody else. And what I'd like to do is pattern this out on a year-by-year basis. So this is 2018. This is 2019. We have certain data points in 2019 that it seems like look like they're in that pre-2019 pattern. And then we have this stretch, and looks like there are a couple of data points in 2021 where they follow the old pattern again. So if I look specifically at 2019, we do have this big increase, this stack change. And if I look at 2021, we go from 2,500, 2,700, 2,800 down to 23, 22, 23. So significant differences at this point. If I break it down by expense category, we can build a box plot this way. And it's hard to see. There are some items here that have a lot of outliers. So what I might be looking for is cases with a lot of these dots. These dots, or these open circles, represent outliers. They are data points that are beyond 1.5 times the interquartile range past the 75th or the 25th percentile. So all of these points represent things that are pretty far out there. They're in the top few percentage points, and they are very far away from the bulk of the data. You can see that, like, for example, OEM body parts, there's one data point. Radio PA, there's one data point. So having an outlier is not a big deal. Having this many outliers, it kind of tells us something. Now, let's look at, this is box plot of amount spent per expense category. And, we do have outliers. We have outliers for everything here. This is maybe not going to be very easy to read. So let's build instead some spark lines. So we're going to show the data set for a few of these expense categories, the ones that seem the weirdest, like glass, windshields, and windows. So we have glass, windshields, and windows. There's only one vendor who sells them. This is where the bulk of the data is. And notice that there's a lot of data way out here. If we look at lights and reflectors, Safety First is one of our lights and reflectors vendors. So we have kind of a spread of data. And for this other vendor, Glass and Sons, we have a lot of data that's way down here and some that's way outside. If we look at mirrors, Safety First, again, has a distribution of data, kind of a hump of data. Whereas Glass and Sons has a bunch of data and then some over here. So their behavioral pattern looks to be different from everybody else who is a competitor in the same category. That's interesting. If we build this out as a box plot, you can kind of see it even more clearly because Glass and Sons has all of the outliers, except for this one. There's one outlier right here. But for everything else, they have all of these outliers. Okay, there's two outliers there. But they seem to be strange. And if we look at Glass and Sons again versus their competitors in the different fields, that behavior is quite odd. So now if we look at employees, everybody's got outliers. Everybody's got amounts spent. There's nothing special here. But if I look specifically at Glass & Sons, prior to 2019, I think we could look at this and say they're all about the same. But if we look in our 2019 and beyond behavior, we have 4 people who stand out. And those 4 people we've already seen in a few instances. So we've seen their names pop up repeatedly. And here, they're dealing with significantly more per invoice. And those are the 4 people versus everybody's behavior. So these are down in this section. This represents the other 8 employees. This represents all 12 employees. And you'll notice that they go back, all 12 employees go back to normal behavior at that point. So these 4 employees are tied in with all of the odd behavior in our data set. So we have this one vendor, Glass & Sons, and we have, this is what's going on with everybody other than Glass & Sons. So it's basically a straight line. I mean, it's a very, very squiggly straight line, but we have no major difference. We have no major gap, jump 2019 to 2021. It's all the same for everybody except for Glass & Sons. And I've got a few other data points on here that basically really tie us down to this idea of there was something hinky going on in the data. And I think I'm going to skip past time series analysis, talk briefly about numeric analysis because we've only got a few minutes left. Technically, I'm over. We're supposed to be in Q&A time. If you have questions, drop them in chat. But numeral analysis, a couple things. Number one is number of round numbers. We would expect some percentage of data points to end in a certain number of round numbers. And there are different types. Like a type 0 is you have no trailing zeros. Typically, when we look at this, we tend to ignore the pennies. If you're looking at dollars, if you're looking at currency amounts, you normally will skip the cents. You normally will stick with just the dollars, maybe round up to the nearest dollar. So if you have a type 1, you have 1 trailing 0, 180. Type 2, 2 trailing zeros. So we have 0, 0 at the end. Notice that this 0 in the middle doesn't matter for the type. So type 2 has 2 zeros at the end. A type 3 has 3 zeros at the end. A type 4 would have 4 zeros at the end, and so on. Second thing I want to talk about is a concept known as Benford's Law. Benford's Law is also known, it's a power law phenomenon. Basically, in cases where you have a large number of, large spread in terms of the numeric values, in terms of orders of magnitude, then given enough data points, they will follow a specific pattern where the first digit will be the number 1 about 30% of the time. The first digit will be the number 2 somewhere around 17, 18% of the time. It'll be a 3 about 12, 13% of the time, and so on. It'll be a 9 the smallest percentage of the time. So it will follow roughly this curve. And this, again, requires that you have several orders of magnitude in your data. So if everything is between $0 and $100, you're not going to see Benford's Law most likely. If it's $0 to $20 million, you're probably going to see Benford's Law in practice. Let's take a quick look at that demo and see how things look. And so I'm going to plot the Benford's Law first, just to show you what the numbers should look like. So I've got a couple of functions. One is this function to plot Benford, and I have the digits. I'm going to plot this out. The other one is breaking out digits, like yielding a set of digits from strings. Let's look at California housing. These are California house sale prices over some time frame. This is a scikit-learn sample data set. And what we see is it's not an exact fit, probably because there weren't that many orders of magnitude. You're selling houses in California, you probably have about 2 to 3 orders of magnitude difference. Most likely everything's above 100,000 US dollars. Most likely, most of these things are below 10 million US dollars. So you're not going to have a huge range to work with. But even so, we do see some shape of this pattern. And these dots are the predictions. These are what we would expect if something did follow Benford's law. If we look at different types of wine, they have values that range from 0.48 to 1680. Again, this doesn't fit Benford's law very well. We have most of these have a starting number of 1. Because realistically, it's like 1 to 1680. So not a lot of differences. The iris data set, most of these data points fit. They don't go above 2 digits. I think most of these are 1 digit. So we have not a great setup. This is not going to be good for Benford's law. We have 1 order of magnitude. But if I look at the list of urban parks by size, this is a Wikipedia data set. And you can grab the URL. You could check that data set out. It's a table there. This is, I think, number of acres. But you'll notice 1 is overrepresented, but everything else kind of follows. If we look at the list of highest towns by country in terms of height, it's not a perfect match, but it's not ridiculously off. If we look at populations, this is typically where you're going to find a better fit. So this is North Carolina's population by, I think it's by county. And we have almost a dead-on fit for Benford's law. We look at the 2019 population estimate. This is a little bit low for the ones, but it's pretty close. If we look at U.S. population, so total census 2010 to 2019, we're going to look at the 2010 population that came out from the United States Census. It'll take a moment for this to come up, but it is, again, going to be pretty well dead on. So I don't know, maybe it's taking a little while for me to download this data set. So I'm going to cancel that, see if I can get back to where we were, because I don't want to have to kill and restart this. Okay. Wake County expenses. This is going to be much faster to grab. Hopefully. There we are. I'm going to plot budgeted amount. Budgeted amount, kind of close. Not horribly off. Actual amounts, again, kind of close, not horribly off. We have a lot of cases. These are radically different data sets, and they're all not perfect, but they seem to come reasonably close. When we look at our bus data set, get our line items, everything's slowing down. This is in total. Overall, hey, look at that. We've got a nice power law distribution. When we look at Glass and Sons, it's a little different. Now, if I start looking at some of the other vendors, in this case, is not quite the power law that we would expect, but it's not too far off. This one actually is pretty close. This one, again, is pretty close. So for each one of these, we're seeing most of these are pretty close, but Glass and Sons, where things were hinky, it looks quite different. So this is not proof. It's not a guarantee. Just because it says it's a law doesn't mean it is a law. It is a principle that comes out of having multiple orders of magnitude and a large amount of data. Now, last digits we expect to be random. It's arbitrary. We should have roughly the same number for everything. Excuse me. So you should have as many zeros and ones and twos and threes and fours, etc. What is interesting, this particular image that I have, this is an example of fraudulent data that was academic data. There was a professor his graduate students were making up data. And the way that you can find that this is made up data is humans are really bad at faking data. If we had more time and a lot of people in here, I would ask people to give me a bunch of numbers, like pick arbitrary numbers and try to be random. And what you would find is that the last digits, instead of being approximately flat, people will overestimate 2, 3, 7, 8. They will underestimate 0 and 5. The reason is having a number in and a 0 or a 5 doesn't feel random to us. And as a result, we undercount the number of items that should have zeros or 5s and overcount the more random feeling numbers, 2, 3, 7, 8. And that's kind of what you see in this data set, where they overcounted in their faking data those numbers. So this is a good case where if you don't have a reason to believe that the last digit should be different, expect a uniform distribution. And if you don't see a uniform distribution, that can be a sign of hinkiness. Maybe not fraud, outright fraud, like in this scenario, but at least a little bit weird. So we're going to wrap things up now. This has been, for some definition of quick, a quick-ish survey of forensic accounting and outlier detection. We focused mostly on Python. We've also did a little bit in SQL Server. You can use these techniques across a variety of data sets. So it's not just finding fraud, but also simply getting a better idea of how to understand what it means really to know your data and go through these different things. Distributions, summary analysis, growth analysis, cohort analysis, looking through all of this, not necessarily from the standpoint of I'm going to find out someone who has done bad things in my data, but more in the sense of I really want to understand the structure of my data. I really want to understand what is going on and the behavioral patterns of this information. If you would like to learn more, if you want to grab these slides, if you want to grab the demos, if you'd like links to additional resources, that is all at csmore.info/on/forensic Python. And if you have any questions afterwards, obviously I'm here for Q&A if you want to ask them now. But if not, please do feel free to send me an email. You can also hit me up on X should you so desire. I'm not that active on there, but if you need me, if you reach out to me, sometimes I'll answer. But those two mechanisms are probably the best way to get a hold of me. So with that, are there any questions?
Okay, so well, doesn't look like anybody's put any in the chat. If you have got a question, you can raise your hand, and we can quickly take some time to answer those questions. If not, you can put them in the chat window. But while we are waiting, we'll give you a couple of minutes. Big thank you to Kevin for giving up his time and taking us through this fantastic session. Big thank you to you all for actually being part of this session. Like I did mention at the start, we have had some people join. This session has been recorded, and I will need to do some processing, but it will be placed up onto the YouTube channel where you can come back and watch this at any point in time. So the YouTube channel was put in there, so feel free to sign up to that. We also put in there the links to the Data Virtualized in November, 6 sessions. Feel free, sign up for that. And FabCon for next year. So no question, but we've got a comment. Thanks for the session and for staying up late. Really interesting stuff. And thank you, Rennie. Anybody else with comments, questions? Otherwise, we'll give you back some time. We've got some applause. Excellent. Good session. Thank you very much, Kevin. I thoroughly enjoyed it. It was a completely new session for me to participate in. So no, I found it very worthwhile.
All right. Thanks. I appreciate that, everybody.
All right. Well, if nobody's got anything else, then big thank you to everybody. I'll stop the recording. Everybody can get some time back, and Kevin can go and get some well-earned sleep.